These are mobile telephones that are handmade by Alfonso and Coque using a Raspberry Pi and Arduino sockets. And then you have the whistle, 2600 Hertz, which will be part of the pack. Okay? Well, Mr. Valero, I think you know him. His presentations always impact me. I'm sure that you will spoil my lunch, but please introduce yourself.
Bajarme 3 pegatinas para Abel, que le vamos a decorar el portátil. ¿Quieres HDMI o VGA? HDMI. Fácil, ¿vale? Aquí tienes el pasa y conéctalo.
Enhorabuena, me ha encantado. Me he descojonado.
He hecho lo que he podido.
No, está muy bien, está muy bien. Te digo yo que este año sales entre los 10 mejores, ya verás.
Buenas tardes a todos, gracias por...
Good afternoon, everyone, and thank you for coming. I'll be telling you about a type of malware that is used for espionage. It's used by states, basically, with very peculiar protection mechanisms behind the scenes. I will not stop here for too long. Abel Valero, I work for Panda. My contact details are there. My Twitter profile. I'll talk about Finfisher. This is a surveillance software developed by a company called Gamma International, with headquarters in the UK and Germany, and a number of subsidiaries. They all belong to Gamma Group International. This is from Wikipedia. Nothing else about them. Towards the end of 2011, there was a leak, an information leak in WikiLeaks, telling us about CNC, how to connect with servers. In September of 2014, WikiLeaks released the binaries for Windows, and investigators started looking at this. Since 2014, different investigators have been analyzing the code that was made public by WikiLeaks. Just scratching the surface in most cases. At several private events, they've been discussing the details about the files that were leaked by WikiLeaks, and then in October of last year, 2017, a paper was published mentioning Finfisher, Black Oasis APT and new targeted attacks leveraging zero-day exploit. In this paper, they talk about the existence of a virtual machine which is used within Finfisher. The MD5 for the binary was analyzed. This is the value. We know that there is a virtual machine, and you know that I don't like them, so I started looking into this. So I started analyzing the dropper part. Obviously, I would open the file to see the structure. Here we see there is just a basic PE 32 bytes compiled with MSBC with all the typical sections for that type of file. And then it has a resource with several entries. As you see, there are some language entries, icon group entries, and configuration files. Here Icons are legitimate, the configuration file I'll mention in a minute, and this will be part of some payloads. So I start looking at the code, and I realize that this is what you can see. There's a jump here, and its counterpart there into the same address. It could be JAB, JAE. It will jump to the next address, whether it was the first or the second one that was executed. In order to continue the analysis, we will have to clean the code, because if we try to look at this directly in the code, we would just see rubbish with invalid instructions, things that make it impossible to read the code properly. And if we want to use kata or AIDA, it will be impossible to read. So we must transform these conditional jumps into unconditional jumps, something which is relatively easy with a number of patches. Let me show you a chart how this has been coded in x86. Here you see how the jump is represented, all the elements and the way it has been coded. 70 JAO, 0F80, well, you see that we can jump to areas that are closer to the memory, or areas that are farther away. It uses an opcode using 2 bytes where it's closer, and for longer jumps it can occupy 5 bytes. You see 0F80, 0F81. These are similar. So changing from conditional to unconditional is as simple as changing 2 bytes. The first one we cancel using 90, and the second one we change by using a 9. This way we are converting this into a JMP. The 0 is replaced by a 90, and the A2 is replaced by a 9. We don't have to do any alterations to the code. The next jump will be cancelled. I'm not interested anymore because both go in the same direction. So 6 bytes, I do the mapping, and the code has a single jump. For shorter jumps, conditional to unconditional, there's only 2 bytes that need to be patched. Here we replace 7 plus something by an EB. So moving from conditional to unconditional. The same we saw before. Here we have 7709 going to EB09, 9 bytes forward. To do the cleansing, we search for patterns. These are the ones. 0F8 whatever, 0F8 whatever. In that mask we can have values, different values. We need to locate all of them and change all of them. Here we have a script, a simple script, which does what we want. Okay, let me explain this. These are macros from R2. /x does a search with wildcards. Find me anything, 0F8 whatever, 0F8 whatever. This is everything it does, okay? Nothing else. The next line. Here we're defining a macro, which does patch 1. Patch 1 will write on that position 90E9, which overwrites the conditional jump and converts it into unconditional. The next thing it does is move 6 bytes ahead and then do the mapping for the instruction behind the scenes. And then I go back to the initial position. And this is where we have the magic. Here a macro is defined, which is executed at the same time. In the first line we did a search. We will have hit 1, hit 2, hit 3 and offset, whatever. Here I'm defining a macro. It's saying that in the full variable it will store the place it jumps to. If it moves from 40 to 100, it will say 40 to 100. If I move 6 bytes ahead, and it will tell me about the destination for the next instruction. Then I go back where I was, and then I do restart. If it gives me a 0, they will both jumping to the same location. If that is a conditional jump, it goes to the same location. There I know, thereby knowing that I am where I want to be. And with the at hit, all of these will be passed to the macro. If the condition is met, with a question mark, exclamation mark, it will execute patch 1. Patch 1. So patch 1 will be executed for anything that meets the requirement. So the code will be cleaned. For short jump, that was for long jumps. For short jumps, it's exactly the same, but looking for the short patterns. The final script looks like this. I said magic. Well, it's not that magic, but anyway. It's about being able to interpret macro formats properly. There's 1, 2, 3, 6 lines. 6 lines gives us everything. So I carry on with my analysis, and these are the functions. This is the start of a normal function. It initializes the registries in the stack, but here all instructions are referenced, and all of them do things that don't make any sense. Here it multiplies something, storing it, but lots of strange things happening. It doesn't add up, it doesn't make any sense. All functions do the same thing. This code makes no sense whatsoever. What we do see is that all the functions end up jumping to 401950. This address. This makes me think that this is the virtual machine they were talking about. This is a function that has its full code, which has been replaced by useless code that does nothing. Because when we get to this point, it does nothing at all. So whatever you did here doesn't make any difference. No movements in the memory. This is just about introducing certain values on the stack. This value that you see here for this function, and calling the interpreter for the virtual machine. Multiple calls to that address 401950, which is a function that will initialize the virtual machine.
Yes.
So this function stores memory and then decrypts the algorithm to encrypt or decrypt the P code, which will be interpreting the original code. It will encrypt the P code, and then we'll see the thread we are in, and then it will compute a value to access to the memory area in the context of VM, and then it will jump to one of the 21 operations available for it. And well, that's all for the VM. And let us say that a month ago was article published. The first name of the article was by Rolf Rolls. It was an article about cleaning the code, and he also published another article about VM. Then parallel to that, ESET published a wonderful PDF explaining all that, how VM worked. Well, when I sent out that proposal, I was told that has been already been published. So if you are interested in VM, so I gave a tutorial about VMs, how to identify them, how to set them up. Okay, so you have information at GitHub, both in English and Spanish. All right, so what did I do from there? So there was a virtual machine, and then I said, okay, what I'm going to do now, because I want to have some fun, I'm going to reset that code. That is to say, I want to get the binary before it was virtualized. So for that, I created a tool. I gave it the name P tool. So then I had an original P tool, then I added the plus tool, and then it supports the different configurations of VM, and I just wanted to obtain binary close as possible to the original one. I turned 40 years of age and I was a bit depressed, and I decided to go for this, to have some fun. Okay, the needs, requirements. I needed to have a PA parser to access the different sections and to rebuild it. I have that library, but also a known library that I built a few years ago, which is still working. So this assembler we have custom, but I have my own one, and the one that I'm well aware of. Then I have a search engine that also allows me to make binary searches, and then I will process it in code C with no problems. And then what I don't have, I just took it from somewhere. I took this compiler, this assembler. I used Keystone, but it failed for me, so I will end up doing Keystone myself. Okay, and then I have Decompiler Routine, is the AP lib by Jerson Ibsen. It is highly optimized and it is very good to compile code. And then I always want to do all this in a simple manner, okay, so that I can go back to it at any time and do not have any trouble. Okay, this is a to-do list, okay, and these are the things that I have to do to rebuild the code. First of all, I need to have the configuration of the VM. Well, they have made a tool that virtualizes the code, but that code is not always virtualized in the same manner. Well, the only thing that they change is the code table. So when they build the second virtual machine, the 2 is a GP, so they just change the table. They change the table and the codes in it, okay, not the actual virtualization system. Then I will have to have the size of the unzipped P code, and then the P code, I will have to find the operations table, that is to say, to emulate it, and for that I will have to cleanse the obfuscation that I told you about before. Then I will have to interpret the P code all at once, just to find out about all the available functions, and then I will have to isolate each of the functions within that P code. Perhaps that's the most complicated bit, but it can be done fast. If I want to rebuild it, like if it hadn't gone through the virtual machine, I will have to take care of relocations, which are values are changed whenever an executable is changed, it moves to different memory areas. So, well, to get the configuration of the VM, I will do the following. I will use this trick. I know that this executable can be relocated in the memory. So some areas of the executable were inserted with location, so they need to find out about the base of the program. So the value that we see here, the 004000, that value changes depending where the image base of the program is. Today is 40, maybe 50, maybe 0. So what I do, I just load the file, I just take a look at the default image base, and I'm going to look for it. So this is the first match. That is to say, these 4 bytes that I have here is the VA. If I add 40,000 to this value, that's where the P code, which has been compiled in the virtual machine, starts. Then the P code will be on top once it is decompiled, and here we have the decryption key. So for also to find the opcode table, I will do the same thing. They said in the offset you have this code 1, 2, 3. What do? I do the same thing because the X can be relocated in the memory. I'm going to look for the opcode table, but I will look it in the high part of the base. I'm going to rule out the low part of it because these jumps are relatively close to each other, and then this pattern helps me find it fast. So I'm going to look only 50, 40, 00, and any value. This is the way it is represented in the memory, and this is the way it is represented. So these with a mask of this kind, XXXX 4000, I will look for the test section of the binary to find the table. Once I have the table, I will have to recognize which each opcode. What do I need to do for that? Well, first, cleaning the obfuscation. My disassembler disassembles instructions, and then I find this the result. If the result of the cleaning the code, I don't want to show it. But if I find a jump which is close, which is 8, 16 or 32 bits, I tell it to disassemble that point where there is the change. So because I've changed the GB to GMP, so that the JMP, I'm not interested in it because it is linear. So from here, any jump which is not 8, 16 or 32, which is a memory jump or far away jump, that stops the disassembling. If I find a conditional jump, I will store it in the table and I will disassemble later on to find out more about the instruction. When I do that, I create signatures in TXT, I store them, and this is an opcode, a full of code, which is a comparison. Notice that in the VM is reading from EAX that has been initialized to EBX. That's where it stores the initial flags. So it is testing the E flags with 800 and then with 80. Okay, so that was for this jump. This is clearly, this is a JZ because it is comparing it against 40. And then we have opcode to emulate code. So all of them have the same format. If I hadn't cleansed them, I would have seen lots of useless jumps and instructions and jumps. But if I repeat the process and if I compare the TXT and if I identify it, I will identify each and every one of the opcodes, no matter how much they've been changed. Then I have a TOT file where I store each of these structures, and that will be used in a giant switch for interpretation. So every time I interpret a P code, it will go through my switch, and my switch will print out, well, for instance, the P code. If I disassemble it, something that I understand, for this is X88. So the code 1 is GL, and the other one is J9. And then I have the parameters of a number of structures, and as I say, that is available in the documents of Rolls-Royce and assets. So these are, I initialize some internal structures to represent all that and to have a code flow. So here I will have to emulate the dispatcher of FinSpy or Finfisher. Well, when I say FinSpy, I mean Finfisher. So we decrypt each of the instructions that we got. So each of them occupies 24 bytes. The first D word doesn't have the XOR applied. The first XOR is an ID XOR. So the dispatcher checks if the value to be loaded in each of the register requires relocation application. So we will try it in the VM, and then if it has been relocated, it has to be detected, and it will show that with a flag. So this is what I do. This is the full function that I will be getting, that will be giving me the full code of the VM code that I will interpret. So decoding the buffer, it is as easy as applying a sure after the first B word, where we have the P code. So we do that for the 5 D words, and then we code it. So this is what FinSpy does to interpret code. So it is checking whether there is any relocation or not. In the byte 6 of where we have the opcode, we see whether the next parameter has been relocated or not. If it is relocated, it will add the value of the base. And then I call this big switch that I showed you before, and therefore it will give me a legible representation of the code. Can you see that? Oh, once I do that function, this is what I get in return. Okay, so this is the P code, this is the ID value, which is never decrypted. Often they are consecutive in 24 bytes, and at the end of the day, this is the code, this is interpreted. This function 4885D2. So I have here all the full P code that I got from the program. Everything that they didn't want us to see, we are seeing it now. But now we have a problem. I don't know where the functions start or finish. So therefore, I will have to look within the D code, P code. I will need to no, in the dropper, Speaker is correcting itself, I will have to find where each function are being called. As I told you before, the important was the value of the push that I did and then the jump to the address. For me to determine the entry to VM, the routine 40, so we have to look for structures of this kind, 84XXXX 0F84, which is the pattern that we are seeing on the screen. And there is another way of calling it is push and jump, and that will give me different values. So when I look for all those values, I will see which ones call the same function most of the times, and then I will identify where the entry to VM is. Then I will just store that push value and also the location of the address, and in this way, now, well, we have the masks in my search engine. Now I've added the masks that I showed you, and every time I would find this rule, it will call this rule, and then I will process it. What do I do? Well, what I told you, I check how many times it has called it. If it does it more than 3 times, I repeat the same step and I process everything again. So therefore, I have all the calls that have been made to the VM, and I have all that stored in a list. And then I will go through the first call. I go to where the P code starts, and I start to decode, and the moment the instruction I am about to decode matches the address of one of the calls that I have, that means that the function has been terminated, because I am going to enter in the next function. So therefore, I know where the instruction have been eliminated, whereas in this case I isolate them, I can rebuild them, I know what they were, and I can put them back. Okay, this is the algorithm that I used. Once I check whether the code has been recovered or not, I repeat step number 1 with all the functions up until I recover a perfect functioning code. Okay, this is the code of my tool that does that. This is the first loop where the entries are generated, where the native code for each of the entries of VM is generated, and if everything is correct, then I go into here and I enter the ranges. So in the beginning, I'm only interested in identifying the sizes, how much the function measures. Well, I do that run again, but this time to generate the code, I apply relocks, and I know the size of each of the function. When I apply the relationship between the instruction and the relocks, I generate the assembler code, and therefore my code is perfect. Okay, now. Okay, this is the part that will apply the relocation. I was about to show you how the tool works, but my Roman told me that I have no time for it. Okay, well, I will show it to you at the end anyway. Well, because if I start to load the VMs now, it will be time consuming. I will show it to you at the end of the presentation. Okay, I have my tool now. Every time I will find code from the VM, I will go through my tool, I will forget about everything, and the tool will give me a perfectly clean code back. Okay, actual analysis of the code dropper. So the code has been rebuilt, no obfuscation in it, and the main function of this dropper is to decrypt the next phases and to inject them in Explorer.exe. So if we try to debug this, will not work like that. If the malware is executed in a sandbox, will not work. So therefore no one will know what will happen. The malware is doing nothing wrong, so that's a good way to bypass. So well, debug actions, be looking for network card to see whether it is in the virtual machine or not. So it rules out things, okay, because it doesn't want to be run in a virtual machine. Then it does a purge to debug breakpoints. So if you purge that API every time that there is a drag point, then Windows calls there. But it doesn't call that because we insert a 90. There is a CC function, so it never stops whenever there is a debug function. Okay, instead of breakpoints, you just replace it with 90. Then and then sets information thread so it blocks the frame so that it cannot receive debugger messages. It also checks whether the debugger port is active or not. So the only problem that we will find within VM if we are not debugging is the first one, the setup API, that we will patch later on. Okay, so I continue analyzing the code. I open up the program again, the deciphered or decrypted VM, and then I see that it has a resource. So these bitmaps will be the payload to infecting the 32 and the 62 system. This payload has been encrypted with RC4. You just take the time data stamp or the header of the file, you multiply it by 2, you apply an RC4, and then you make that you can decrypt the resources, and then you will end up with a binary. So you can do that for 32 and for 64. I will focus on the 32 bits part. So the dropper will inject in the Explorer what I have just found out or take out from itself. That is to say, the DLL that will continue with our patch, okay? So this injection system has been interesting, has called my attention. Well, surely some of you have seen it before. I hadn't seen it before. So at the current process, when you are executing the malware, which is its own process, it will obtain the user32 address. And now, notice what it does. It reads that address within the Explorer process. I was shocked by that, and I said, well, Windows, when the system starts, uses user32, kernel 32, and NDTL are always mapped in the same direction for all the process when the system is started. So if you obtain the base address of DLL, you will find that very same address in any process that you may open for using 32, for kernel 32. So they read the user 32 of the Explorer, they read it to the current system, they patch the third entry in the test system, which is a dispatcher of messages. When that's the function that sends out messages to the Windows function. It is patched so that it points at their own code, and then they stop the Explorer, they demap the original section in Explorer, they demap the user32, and they map the one that they have patched. So by the time they will restart the Explorer system, they will see that the function that used to do the dispatcher of the messages that go to the Explorer will go through the code that they have injected, and then the code will resolve the payload that has been just inserted in Explorer. If that payload, as we are seeing now, well, we can dump it, no problem. We know where it comes from. It comes from these resources. We know which is the encryption key, so we don't need to dump anything. We just rebuild this as it is, and that's it. And then we move on to the next phase, which is the payload in charge of infecting 32-bit systems. So whenever a Windows program has to call functions, there are tables to call to. So you see these odd values where we have a VA, which is pointing to a part of the X file with a text string. So they have replaced the VA. The address has been replaced with CRC. They said, okay, CRC, instead of pointing to the string, to the chain, okay, you point at the CRC. Because if you try to insert this in the memory, it will exploit, it will just burst, okay, because it doesn't know how to rebuild that code. So reconstructing or rebuilding IAT. If we know how RC works, we will have the time to build another tool. So this is the function. A CRC function is just a short, well, from the previous value and the current value, and that's it. And then the tool that I will be using to reconstruct my IAT will go through the payload of IAT. I will obtain the name of DLL. I will do the load library of DLL. I will obtain the first trunk CRC, and then by the time I will do that, I will check the CRC, and then I will name it. And then now I have this program So it should point to what it says main set. So once we have that, we have the IAT already rebuilt. And now let's take a look at the file, see what's in it. Again, typical sections. And we have these sections where we have 2 resources and then an icon section. So this DLL will we take care of the infection process. First of all, we'll get some parts from the resources of the files. The first thing that we'll do, we'll open icons, we'll decrypt it with resource routine, and once it will be decrypted, so that file, it is like installation configuration, has name of files, and then it reads part of that config file. It will record that very same file, but this time encrypted with a key that it will take from itself, and then it will record it, or it will save it as xxx.cab. And then the name of the directory is hit service. It will create the hit service folder, and xxx will be the date of the system, okay, since when the system was started. Okay, it will decrypt this section with no name. That section will be decrypted, and it will be written in a disk with a key that has taken out from the file that was read before. It is a key with 256 bytes. So this file, it is written on the disk. So these people have a solution. They set up a number of configurations so that a batch of Finfisher doesn't include the same directories always, so that it is more difficult to find. So the initial part of the payload is about generating config files and folders. Once it will go into persistence, into actual infection. Infection can be carried out in 2 ways. When the program was run, if the user was an admin, okay, so you have made it very, very easy for him. If you are in Windows 7, X32 allows you to install drivers. If you install drivers with no signature, so let's say this text, okay, I have a admin privilege, good. I'm going to take out resource 101, I'm going to code it, and that resource is this is a driver. So it installs as a service, system service, and that's it. If you're an admin, but if you're not an admin, it will do it in a different way. It will take out from resource 101, it will take the driver hit service sys. Then it will look for a mask, okay, 8 Fs, F letters. And then when it will come to the points, we will see that another driver starts. That driver will be mapped in the memory, will go to its resource, and it will take out a DLL. That DLL will be written on the disk, and then it will extract the resource 103, and it will also write it on the disk, and then it will generate this register key. So it will include the DLL that had been extracted. For it to be, it calls run DLL control. So it has just established the loader to charge this, or to load this payload. If the system is Windows 32 and can use that driver, well, the actual driver will do all this. By the time the system will be run again, the driver will take out the driver that it has inside, and then that second driver will take care in the logon Windows or Explorer, it will install it. But if it doesn't have the privilege, will do the same thing but through Explorer. I'm not going to complicate my life, and I'm going to analyze the second part. So summary, creates the config files, the write persistence, takes out the binary files, CRT CLI DLL, or extract his service and install it as a service. One of the 2 things will happen through that payload. Let us see what CRT CLI does. So, what a coincidence. It has a VM. It's not a problem because we have our tools, so we don't mind about this. We just ignore that DLL. So it reconstructs all the virtual functions. I will show that to you in the demo. It will restore all the bytes. So notice that DLL has lots of code that has been eliminated and that I rebuilt. Once it is rebuilt, I can analyze the DLL, and I can see that the only objective is to read from the disk the library MSVCR90 and to inject it in Explorer, and uses the same techniques, uses the Explorer, the hooks, loader, runs it, and that's it. So it also has an anti-hook technique, which is quite typical, which is to say it loads the libraries that uses the process it uses, it maps them in the memory, and then it checks the actual one for the system. And then said, okay, let us see if some of them has been parched. So if they have been parched, it can see that it is trying to hook the APIs and then stops working. It obfuscates the calls to APIs by mapping the memory disk, and then it does like trampolines. Instead of calling the jet version as mapped in the memory, I will call the jet version of the DLL that I mapped manually, and that will call the actual address. So you will always see a memory which is not the typical one, and then you will see lots of functions and names that do not really make any sense to them. And now, when I take a look at hit service, and I say, well, something looks odd to it, it's like a driver with another driver inside, a DLL. Well, I have my tool to extract it from virtual machines. Notice the code that has been rebuilt, 18 bytes, 36 bytes, not very lots of code. So, well, the code decrypts other drivers in the data section, loads it in the memory, and runs it. That's the only thing it does. So this driver is a persistent system. Let us take a look at the second driver that was taken out. If we analyze it, we see that there is a section for resources where we see a bit file. It uses VM, no problem for us because we rebuilt it again. Notice it has rebuilt several blocks. It is a bit longer now. So this driver will decrypt MSVCR90. So notice this is the it will inject it in WinLogon. So it will not be necessary for us to run anything in this driver because the actual loader knows how to decrypt it and everything. So we will be using the same method that it uses for decrypting it, and we will obtain it. What we will obtain? Well, MSVCR90 DLL. This DLL, again, has been compiled with VM. Okay, we remove it. So we don't see, well, this one didn't have lots of code either, but enough not to be able to analyze it. And now the objective is to decrypt the DLL of Finfisher to do the espionage activities for us. So it will give features, protection or secure features. So this DLL is an injector, is a loader, and it is also a protector.
So if we take the DLL from Finfisher and we load it directly, in theory it will work, but there are some things that we have set aside because of the specific characteristics of this DLL. This includes the final DLL from Finfisher. Let's take a look at the protections. This is something that I really liked. The first thing after injecting is intercepting this key user exception dispatcher. Any exception within the Explorer will be treated by the injected code. A screen pop up telling you whatever is happening. So this is intercepted. Now when it starts loading the final DLL, it resolves it manually. So it has to resolve its imports. It hooks them directly. These three APIs during the resolution of Finfisher DLL are intercepted. The three APIs are intercepted: Virtual Protect, Reset DCW, and Delete DC. In any analysis that you carry out, of course, of Finfisher DLL, you will have to take into account that whenever we make calls to these APIs, these are not the original APIs from Windows. The hook virtual protect, what it does? Well, you first call virtual protect. It will do a visual query to different memory addresses. It will find out whether these are executable, and if so, if that is the case, it will allow the permissions to be established. Hook delete the Z. Things are beginning to make more sense here. This hook establishes other hooks like create thread, terminate thread, and exit thread. So it controls the creation of threads in the process. As a parameter, a code is passed to this function. What does the function do? You call the function, you pass it the payload, it takes the code, it encrypts it, and there will be a location in the in memory which you will not be able to access. Every time you call the function, it will create the threads and suspend them. It will protect the code by encrypting it, and finally adding permissions, non-accessible permissions, and then it will execute the thread. What will happen? Well, a full mess. When this is executed, the system will say this is a paging error. If you manage to apply paging with forensic tools, this will be encrypted. Why? Because you are supposed not to see anything strange. Within Finfisher, when we see that call, we will know that it is protecting certain memory areas. And then hook reset DCW. This is invoked to deactivate and release the memory that we indicate. As a summary, virtual protect is hooked so it doesn't disturb. Delete the Z is in charge of protecting payloads in memory by encrypting and eliminating the read permission from the memory page. Reset DCW is in charge of reverting and releasing memory and payloads that are protected, and Key User Exception Dispatcher does what we have just seen. Here we start the analysis, the proper analysis of Finfisher. Here I'm flipping out. Five previous payloads were passed. In theory, this was protected in memory. But if we have obtained the DLL, we will see this without any problems. So now that we have the DLL, since it was not encrypted, I'm not sure you can read it, but this is wonderful. This is what the DLL does. It records emails, it records details on the Wi-Fi connection, it records the passwords, it's got a keylogger, it has controls for voice over IP, mouse events, it records anything with a webcam, it records anything on the screen. If we have a mobile phone connected, it records all the events. It can even find out whether the computer has forensic tools installed. Change file records. An audio file can be uploaded saying it's ours. They can read data from our Skype. They can print, they can delete. Well, I wonder, is there anything they cannot do? Clear text, by the way. If you dump this when the malware is active, you will see nothing, but with the DLL, you can get it to it. So all of this code can be read. Its protection was applied to the previous stages and onto the virtual machine, but here there's nothing. If we get the DLL, the party is on. There are two phases for the DLL. The first one will be DLL main when it is loaded into memory, and the second one is run DLL, which is invoked, as we saw before, with the corresponding option. DLL main. This will initiate reading the virtual files. If it accesses payloads, those payloads are not in single files, in unit files. I showed you before a file that was written into a folder, and this is a container for a virtual file system. In order to access this will hook all the APIs for disk access. Create file, delete file, get current directory, copy file, well, anything you can imagine. And then it will hook create process W and create remote thread. Hooks to APIs for access to disk are established in order to use an encrypted virtual file system. Open7f, for example. If you try to open the file using Windows, you will not open anything, but the system will check the virtual file system to try and find out a 7f file undecrypted. The rest of the hooks is for the protection system brought about by MSVCR90. When you execute hook create process, usually make a call. What the hook does is create the process but suspend it, so that you can apply the protections that you need in order for it not to be located in memory. That's how the system works. You may indicate the parameter and everything will be executed in a suspended fashion. Second stage. Bear in mind that all these APIs are within Explorer.exe. It lives within the Explorer, so it will open up all of its components. Resource 101, that's a communications proxy, which will be injected into Explorer.exe or rshell.exe. Why in these applications? Because they usually have access to the internet. RSHell is for remote control for Windows machines, Windows Mac, Windows boxes. So it's either Explorer or rshell. Nothing suspicious because it's an internet browser browsing the internet, so it makes sense. And then there's another payload, Res 103. In this infection, this is called network map ARGI, injected into all processes. This is like a keylogger, a global keylogger. Finfisher includes initial payloads, but then it can download many more payloads to include all the functionalities that we saw before, screenshots, recording conversations, and so on and so forth. And then the file that I mentioned before, setup cab, where we have all the files for all the payloads. If in the next stage the tool wants to take a screenshot, it will download it, and instead of saving it to the disk, it will include it into its virtual file system. It will be encrypted, so you might open it and you would still see nothing. How about the virtual file system? Well, we have the payloads that will be injected into specific processes. We have the configurations for the malware itself. We have the CNC for downloads and the processes to be intercepted. Within Finfisher itself, dumping setup cab is relatively easy. We can read it, we can see it decrypted, because the DLL does everything. I analyzed the routine to access this virtual file. This is very simple. We have the CSC, we have the size, and then we have a field indicating the size of the file and the start of the next file. So by using this, we see that we have this file, FE0, and all of these things. Files with the suffix 0 are configuration files for IP addresses, environment variables, whatever. And files with suffix 2 are executable payloads, DLLs, which have the corresponding VM inside. No problem, because we can extract this. Let's take a look at the configuration file, because it's quite interesting. This is a file, as it is, which has been compiled, JSON compiled. So we've got a section called TA underscore MIL 1050, where they have the servers they could need to connect to. These are the current servers that were live at that time. The malware is connecting to. And then it's got a section with additional services. Let me just go back to something because I wanted to show you. Right. Can you see there? Perfect. Here we have the CNCs it will be connecting and the processes to be monitored. All of these. Task Manager, Windows Task Manager, inside, well, you name it. There's monitor, blah, 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 blah. How about sniffer? Well, let's control sniffers. Wireshark network analyzer, whatever. If you apply forensics to this computer, a payload will be injected into Wireshark, so you will not be able to see the traffic. That's how it works. If you use debuggers, same story. Interactive disassembler, WinDBG. Browsers, okay. Let's plug into them. Let's get all their credentials. Firefox, Mozilla, Firefox, Explorer, Windows Internet Explorer, whatever. Messenger applications, well, let's get all of them. ICQ from last century, Skype, Whitepager, Yahoo Messenger, Bodylist, Trillion, Google Talk. Mail clients, all of them. People are exchanging files. Well, let's go for all of them. BitTorrent, uTorrent, muTorrent. And if people use voice over IP services, well, let's go into them. Xlite, Mercuro. As you see, they control absolutely everything in the infected machine. Okay, let me go back to the basic structure. Okay, and reaching the end. How much time? Well, I will not show you more payloads because it would be too much. I just wanted to show you how they have done their best to protect this, and yet we have been able to extract the information we wanted to look at. When infecting a 64-byte system, things are almost identical. The virtual machine is different for 64 bytes, obviously, because instructions are different. However, I would say that whoever implemented this VM leveraged whatever was there before, and it's not the same person. This 64-byte machine, moving all those registries, well, it doesn't say anything about that. There's push and shut, that's it. It seems that they had an intern in place, and the guy used another methodology for implementation into 64-byte systems. Adapting the B2 Plus tool to a 64-byte environment so it was relatively easy getting all that code. We've seen how these guys over at Gamma have implemented a lot of defensive mechanisms to hide the final DLL. Unfortunately, those protective measures have not been enough, and it's been very well implemented. The virtual machine has been very well implemented, but in a scale from 1 to 10, I would give it a 4. There's lots of things we've been able to see by looking at this. So there's quite a few limitations. Bearing in mind the opcodes that they have included, another thing. So this virtual machine is something that could be analyzed by any of us. In fact, I would encourage you to take a look at the virtual machine, following this methodology or any other methodology, for that matter. And what on earth is this wooden horse thing? Well, these guys, they took for granted that their security measures were more than enough. But when they initiate their system, they have the wooden horse. I would say I'm a Trojan horse, making it very clear what I am. They said, I have all the protection in the world, no one will look into it, and then I have a sense of humor. So how about using the wooden horse? Well, that's what I found. And that would really be the end of my presentation. I hope you're not dozing off. Let me show you the demos. Let me show you how it works. Perfect. Here we have this file that you saw at the beginning. This is the binary. And this is obfuscated completely. Here you have the rebuilds as given by the tools. P-tool plus is my tool. So that's it. Input file, output file. So I run this. And I do a request. I execute it. It's cleaning the code. It's getting rid of all that rubbish. I'll explain it step by step, okay? Let's just finish. As you see, it has to clean 121 and 29 routines. It's still working. There we go. We're done. I don't know how long it took them to build this virtual machine, but deconstructing it took me a very short time. Not all. The first thing is to identify the opcodes. I have a txt file where I have all the definition for all the opcodes. Opcode 0 points at this address, opcode 01 points at this address, and so on and so forth. And then I identify the basis for the virtual machine, whatever it is, obtain the key, the P code. I apply the cleaning process for the jumps. This would just clean the code. And then in each compilation of the programs where they want to obfuscate, this is the opcode table they want to move. Here the opcodes are the same. The opcode in the table is 0, which is the same in my dictionary. Okay, they're all the same numbers. This is what I use for the patterns. And then finally, what I do is define the process, reconstruct the code, apply locations, and that would return a binary which is executable. This is where this was at the beginning, local. Now I've called the code that has been reconstructed. Okay. And little else. I'm going to reconstruct several other files. This is the same. Okay, I'll use this one. I'll call it driver root dot rebuild. So I'm rebuilding the code. So opcode 0 now corresponds to the number 5 in my table. Number 1 corresponds to number 3. The table I've got here, let me show you. I only need, well, my utility needs this, and then a file, opcode sys, which I mentioned before. This is simply, right, it's just a dictionary. How we would call the opcode. I'm sorry you cannot see everything. Let me just scroll up. Opcode F has the representation. Opcode 5, what you see below. I'm disassembling. I'm comparing character per character. Two little things, two additional things, not so relevant. This is what we have rebuilt. Now we have a file that can be executed. Don't take my word for it. I'll execute it now. I'll now get hold of the first file that was decoded. I'll execute the dropper as it comes from the internet, and we'll see that there is no infection because it will detect my virtual machine. Next, I will use the one that I have rebuilt. I'll patch the byte detecting the virtual machine, and then we'll execute it to show you what it does exactly. This will take a while. My hard drive is not the fastest in the world anyway. This is in user mode. This is in local mode, the high service folder. I'll copy here. This is the original bug. I was downloaded from the internet. I'll call it bug.exe, and I'll execute it right away. So why is it doing nothing? Because it's detected a virtual machine. Why is it taking so long? Well, because there's a virtual machine that it's slowing it down. You see the difference? There's no file created here. Nothing has been created here. I'll take the rebuild part. This has been patched, just 1 byte. We'll compare this file with the one we have just rebuilt called rooted. Okay. So jumps are changed. I'll ask it to find differences. Here we are comparing the one we have patched with the one I have just rebuilt. So we'll do this, we'll execute this. Control C, Control V. Where did it paste it? Okay, that's perfect. I'll go into the desktop. No, doesn't make any difference. and this one will execute. Deleted, no longer there. If we go into this folder here, we see this directory with all the files that I have mentioned throughout my presentation. It's a virtual file system with the setup and everything else. This machine is now compromised and is trying to connect to those servers to try and tell them that we are really cool. And this is everything I wanted to show you. I hope you have enjoyed yourselves.
Alucinante, la verdad.
I'm flipping out. Any questions? There's a question up there. Oh, sorry, I didn't say anything. Mark wanted to say something. Oh, by the way, it was Mark that taught me about this. I learned everything from him. Abel, man, this was so impressive. Really? If you had told us lies, we would have believed you anyway. This is so stunning. Anyway, you mentioned this before, but I have two questions. Compared to other virtual machines, like the one used by Kims and other malware types, is this as complex as the other ones? Kings, I've never looked into it. But this virtual machine is a virtual machine for children, really. I mean it. I said before, Valero was a challenge that we did for a CTF. That virtual machine has more encodings and more instructions than the one we've just seen, and that was for a CTF. Someone who is getting paid a huge salary, I don't know how the price for this bug from the Gamma guys. I'm sure it's a six-figure amount. I can't understand why it's so simplistic. And the second question would be, do you think the effort in creating a virtual machine like the one they use for Finfisher pays off compared to other protection methodologies? For example, with a packer or other things? Yes, no doubt. Even saying that this is a virtual machine for children, any solution for system monitoring, any emulator which tries to emulate the code will not be able to emulate that. This is really a very well hidden element into the depths of the system. It is very well hidden. If you recompile the binary, it cannot be captured by anything unless whoever is trying to get to it interprets the VM properly. I'm sure that lots of people here have got offers to do Black Ops in exchange for a lot of money. There's a question at the top. Hi. I work in system protection. And my question is, with the sysmon from sysinternals, there is tracing the opening of a file, the loading of an image. For example, when loading images, we will verify that there is a signature. The system will verify that there is a signature from Microsoft. Would this detect it? In this CVR, whatever. No, you won't detect it. Let me tell you why. Because these are injections that are done manually. There's no load library, okay? You could detect it if you apply rules. When assigning memory to a process, there you would see it, but you will not see the load of a DLL because there's no such load. These tools map the memory into the process. If you did a hook or you investigated the API or the open process, there you would see how things are being written. But you wouldn't see a library being loaded. So you need to activate the trace. You need to activate the trace, creating remote threads and so on and so forth. Writing memory for certain processes, that is important to detect this type of things. Well, you made me a little bit nervous because we've seen some strange alerts in certain computers of unsigned loads. It may be. Here you wouldn't see loading events for unsigned elements because of the way it works. You wouldn't see those events. Have you investigated the entry point? How does it get into the memory directly? As I saw in that paper, the entry point is a 0-day. Let me think about it. Can't remember right now. 0-day in something to do with the browser. They execute the main exe file and it does everything else. Last question before lunch. Hello, this is really impressive. I have quite a doubt. As I understand it, this type of companies, when selling products to their customers, if a customer makes a mistake and attacks the wrong person, that malware sample should be taken into account for other customers using the same product. That's a comment. My question is, in using this virtual machine, have you found any other samples where the OP codes have been changed in a different way so that a mistake made by one customer is not reproduced by other customers? This virtual machine was created in such a way that in each compilation of Finfisher for each customer, the result is completely different from what you have in other customers. So if this has been leaked, and you know what the file structure is, and the order of the opcodes, that will be very easy to locate. In fact, there is a customer is mentioned there, but each compilation for each customer has been customized. It uses the same VM, opcodes are always the same, but there is a reordering of the table, okay? And then because there is this obfuscation, branch obfuscation, each analysis system will have difficulties when analyzing similar samples. In that sense, they have made an effort generating customized implementations for each customer. If you compare two customers with each other, you will only infer it's the same VM, same code, but you'll need to get all that code. So they do pay attention. And that's why that VM has been designed that way, that everything will be hidden for a long time. That's the main purpose of this tool. Very well, thank you so much, Abel. Spectacular.